our discussion. And on the IV characteristics, this is part 2. And from this section, we are going to switch the reference textbook to this Sedgwick Smith, because from this section, we are going to move from the devices to the circuits. So we are going to talk about the circuits, like the inverters based on the transistor, two transistor. So we are going to switch the textbook. And we can have some reviews of the device structure, the MOSFET. We talked about this before, and this is another cartoon figure. So here we have those geometry parameters, like the width, W, of the transistor, and then the L is the channel length between the source and the drain. So those are the geometry factors, W and L. W over L is important. And then we have the heavily doped source and drain. And this is N-type MOSFET, or NMOS. So the doping of the source and the drain will be N-type. And then the channel or the substrate here will be P-type. So the transistor actually are 4-terminal devices. Normally we only talk about the gate, source, and drain. But actually, to the substrate, P-type substrate, there's a body contact. So this body so if we draw the symbol of the circuit, then we will have those 4 terminals here, for those 4 contacts. But normally for the NMOS, the body and the source are tied up together, and those two are grounded. So the source and the body are typically grounded. So this is the cross-section of the MOSFET, and we have seen this before. So we have the source and drain, and then the channel region, and then here we have the oxide, separate the gate and the channel. So gate is metal, oxide is, for example, SiO2, and channel is the silicon. So this is MOS structure along this vertical direction. And let's review the principle of the operations. So if the drain voltage is 0, you only apply the gate voltage. And then here, when you increase the gate voltage, you will first create the depletion of the channel. So then, once your voltage is larger than threshold, you are going to create this inversion of the surface. And this is the channel with the electrons in this case. And this white region is a depletion region. That means you only have the dopants, the charge from the, in this case, Na, the acceptors. And then you apply the drain voltage. So the electrons will move from the source to the drain, or the current will flow from the drain to the source. So this is when you have the current, and since the drain voltage is small, so this is a linear region, or the trial region. As the drain voltage increase, so then here the channel, the electron density in the channel will become non-uniform. Towards the drain side, the electron density will reduce. So this is this first non-channel MOSFET model we discussed before. Here are the assumptions we have. So we assume that the current is controlled by the mobile charge, in this case, electrons in the channel. And then the gradual channel assumption means the vertical electric field will determine the channel electron density. And then we can get the mobile charge, in this case, electrons, through the voltage difference between the gate and the channel. And then the last assumption is that the electron velocity to the horizontal direction is determined by the drift. That is due to the natural electric field from the drain to the source. So this is the drift assumption. So this is the assumptions we have, and then we derive the IV equations based on those assumptions. So we have done that using the average electron density to the middle of the channel. But here we can redo the derivation again using more generic formulas. So here this is what we know. Let's say the charge of the electron density as a function of the y direction. Here the y direction is this direction. So as a function of the y direction, it's determined by the voltage difference between the gate and the channel. So that is determined by the VGS minus threshold. First we need to overcome the threshold. And then the voltage of the channel tension is a function of the position y. Because you have the drain voltage will drop across the channel. So then the Vy is different depending on where the position is. So then you will have the actual effective voltage between this capacitor, MOS capacitor, that is VGS minus Vy minus Vt. And then we know that the current is determined by this charge density times the width of the transistor, which is in the third dimension. We have this dimension. The wider the channel, then the larger the current. So then you need to multiply the W. And then how fast the electron move, that is the velocity. And the velocity is given by this mobility times the electric field. The electric field is from the drain to the source. So this is the assumptions we have, and then you can get this formula. Drain current equals to COX times this voltage current times the mobility times the electric field times the W. That's the width of the transistor. So then what you can do is to do the integration over the channel direction from 0 to the channel length. That means you integrate from the source to the drain of this formula. And here what you can do here is this electric field is the horizontal electric field. That is defined as a derivative of the voltage at the position y. So you can plug in this one. Then you can get this formula. Basically you move the dy to the left hand side. You still keep the dv to the right hand side. So this is a differential equation. But you can do the integration on both sides from the source to the drain. So the left hand side is with respect to the distance from source to the drain. You know the distance will change from 0 to the channel length L. That is how the distance change from source to the drain. So you integrate this. And on the right hand side is related to the voltage. And you know from the source to the drain, the voltage will change from 0 to VDS. And the distance changes from 0 to L. So that's why you integrate those here. So this is when you integrate from the source to the drain. the distance will integrate from 0 to L, and the voltage will integrate from 0 to VDS. So if you do this integration on both sides, then you will get the equation for the transistor. This is what we derived before. So this is another way to derive that equation. So on the left-hand side, you will get L. On the right-hand side, then you need to integrate the voltage. So the VGS need to multiply by VDS. And then here you have the first order term of the V. If you integrate that, you will get the second order term. So this is how you get this equation, some math here. So I don't require this derivation, but this is another way to derive this equation. You have this equation before. So if you look at this electron density over the channel from the source to the drain, the electron density will reduce as we approach the drain side. But the current is continuous, right? So the current, no matter where you measure it, towards the source side or towards the drain side, the current is continuous. So the product of the Q and E should be a constant. Because here, the current, you see, is Q times the V, velocity, but you know velocity is mu and E. So that means Q and E, this product, should be a constant, because current is continuous. The charge is decreasing over the distance from 0 to L. That means the electric field will increase from the source to the drain. This also agrees with the band diagram. If you remember the band diagram, you have this kind of band diagram. Yeah. So you will see that the slope is a field. The slope is a field. As you go from the source to the drain, then the slope is larger and larger, so the field